Uh, Maybe we can start because we have enough audience now.
Okay, no problem.
Okay. Okay. Hey, share the screen, then I will introduce you, and then we will start.
Okay. Can you see my screen?
Yeah, full screen, it would be better.
Yes.
Okay, welcome to our Majorana-Raychaudhuri seminar series today. Today, our speaker is Professor Soma Sanyal from School of Physics, University of Hyderabad. And Professor, the screen is yours.
Thank you very much. I would first like to thank the organizers for giving me an opportunity to present our work in this Majorana-Raychaudhuri seminar series. Today, I will be talking about magnetic fields in cosmic string weaks. Now, magnetic fields are there in the universe, and we know about it from various observations. In this particular work, what I will try to discuss is the magnetic fields which are generated and evolve in something called cosmic strings, the wakes they generate. And I will try to discuss some of the recent work that our group has been doing in this field. This is the plan of the talk. I will give a very brief introduction to cosmic strings and other topological defects. I will talk about the different experimental observational signatures of the cosmic string, like gravitational lensing, and then I will talk about the wakes which are generated by these strings. There are also several predicted signatures of cosmic strings in the CMBR, that is the cosmic microwave background radiation. All this will be more or less a review of the work which has already been done previously. These are there to motivate, and that is why I will not go into too much details of these things. There will be enough references provided, and people who are interested can go and look at those references. I will then delve into our own group's work on magnetic field production due to the motion of these cosmic strings, the evolution of these magnetic fields in the wakes of the cosmic strings. I will talk a little bit about length scales and the breakdown of Alfvén's theorem. Finally, I will discuss some possible electromagnetic signatures from these magnetized wakes which have not been predicted before, and then we'll see what is the path for going forward. So I start with the very basic things. What are topological defects? Topological defects arise in various symmetry-breaking phase transitions. As an example, I have shown the ferromagnetic phase transitions on the first figure. As you can see, at t greater than Tc, we have all the magnetic moments aligned in all possible directions, which means that the global rotational symmetry is unbroken. However, after a phase transition, all of them are aligned along one particular direction, and the global rotational symmetry is spontaneously broken. Now, this is one of the simplest examples of a symmetry-breaking phase transition. There are various different symmetry-breaking phase transitions, and it may so happen that when the phase transition occurs, some region of the space may get trapped into the old phase, that is the unbroken phase. It cannot move to the new broken phase because of energy considerations. So within a new phase, we have one region which is of the old phase, and hence it is called a defect. Since it is energetically stable, that is why it is called a topological defect, and it is very difficult to remove it from the system. While these two are from the condensed matter physics examples, we have several symmetry-breaking phase transitions predicted in the Big Bang model of the universe. And For example, the gut phase transition shows SU5 symmetry breaking into SU3, SU2, U1. And so we have many different kinds of defects which may be generated due to these symmetry breaking phase transition. On the right-hand side, I have shown the figures for some of the defects and the potentials that give rise to those defects. So we have the first one as the domain wall defect. The second one is the one that I am interested in, that is the cosmic string defect, and we'll come into that defect in more detail as we go along in the talk. The third one is the monopole defect, and if you are interested, you can read the very nice book, Cosmic Strings and Other Topological Defects by Willenkin and Schiller, which gives all the details about how these defects are formed. These defects may be stable defects. There are certain defects which are also unstable defects and which decay away as the universe evolves. So we go to the cosmic string defect, which is the defect of our interest. And the previous picture was a two-dimensional picture. Therefore, it looked like a point, but in three dimension, it will be like a line-like structure, or in some cases where the potential are like the abelian Higgs potential, you will have a radius and it will be like a cylindrical string. So these are what are called the cosmic string defects. As I've mentioned, depending on the potential involved, there can be many different kinds of strings. And some of these strings, like the abelian Higgs strings, are stable, whereas some of the strings, like the electroweak strings or the Alice strings, are unstable. So there are various different cosmic string defects which can be generated from different phase transitions. Even the gut phase transition generates the cosmic string defects. And we will be looking at one of the particular cosmic strings called the abelian Higgs cosmic string. The abelian Higgs cosmic string, or the Nielsen-Olison strings, are generated by the given Lagrangian. The Lagrangian is quite familiar, and as you can see, they will give rise to gauged cosmic strings. Since there are both scalar and vector fields that are present over here, the cosmic strings generated by this Lagrangian usually have a finite radius and extend from horizon to horizon. The long strings which extend from horizon to horizon are stable. Sometimes loops can also be formed. Actually, what is formed is a defect network. So there will be long strings, there will be loops, and there are certain groups studying these networks as they evolve in the expanding universe. The interesting thing about the cosmic string is the cosmic string matrix. The space-time around this cosmic string is locally flat, but globally conical. By this, what we mean is that if there is an ant walking close to the cosmic string, the ant will feel as if it is walking in a straight line, whereas an observer who is looking at it from outside will see that the ant is actually going in a curved path around the cosmic string. So generally, the cosmic string metric is represented by cylindrical coordinates, and we have a flat metric. Only the theta, that is the angle, will not vary from 0 to 2 pi. There will be a small deficit angle, which is shown in the figure, and this deficit angle is determined by the symmetry breaking scale of the phase transition. The mu that we see here is the mass per unit length of the string. This is actually very small for strings that are generated at high energies. So typically, if the cosmic strings are generated in the gut phase transition or around about the electroweak transition, the energies will be of the order of 10 to the power 16 GeV or more. And therefore, the angle theta, the deficit angle, would be of the order of 10 to the power minus 6, minus 7. So it's a very, very small deficit angle. However, the important thing to note is that though small, the deficit angle is finite. And therefore, any particle or any photon going around a cosmic string will appear to bend around the cosmic string. This has given the fact that one of the very important observational factors of cosmic strings, that is the gravitational lensing. So as I mentioned, the geodesics of the particles in the cosmic string spacetime are bent due to the presence of the deficit angle. If these particles are photons, then if there is a source, like the quasar shown in the picture, which is emitting these photons, the photon trajectories will be bent and it will appear as if there are two sources behind the cosmic string instead of one. This is known as gravitational lensing. And other than cosmic strings, there are other objects also which give rise to this gravitational lensing. The distance between the two objects will determine the symmetry breaking scale of the cosmic string, because that is what determines the deficit angle. The other effect of having this conical space-time is the generation of wakes behind cosmic strings. As the long strings move along the universe, as we can see from the picture, those two lines represent two massive particles. And the gray area is when the two lines meet together. So the two particles coming from two sides actually meet at the back of the cosmic string. So there is an overdensity or a wake generated behind the cosmic string. Again, it is the deficit angle, which is the angle of the wake, the opening angle of the wake or the wedge angle. And it is given by the velocity of the cosmic string, which is Vs. Most of the cosmic strings are supposed to move at relativistic speed. So there is a gamma s. And we have the deficit angle part, which is 4 pi g. Generally, it is seen that the overdensity is at least of the order of 1. But in most cases, depending upon the nature of the string, it can be much greater than that. The reason why we say depending on the string parameters is because there are weakly cosmic strings, which are cosmic strings with small scale structure. And these weakly cosmic strings have overdensities which are higher than simple long cosmic strings. So therefore, depending on the cosmic string that we will have an overdensity coming in the wake region. Now, since, as I mentioned just now, the cosmic strings move with very high velocities, when the velocities go beyond the sound velocity, shocks are generated behind the cosmic strings. These shocks have been studied in detail, both numerically and analytically, but most of these studies have not included the magnetic field. Mostly they are studied using the hydrodynamic shock models. And interestingly, it is shown that depending on the nature of the cosmic string, you can have baryons being trapped inside the shocks so that there is an enhanced baryon to dark matter ratio, or you can have baryons which are ejected or moved away from the wake so that the ratio is opposite. So these shocks give a lot of information about the symmetry breaking phase transition which generated the cosmic string. There are several effects of these cosmic string wakes, observational effects. The cosmic string wakes, as I mentioned, generate these density inhomogeneities. A density inhomogeneity is like a very large scale fluctuation of the density. So at some point of time, they were considered to be the generator of the large scale structure of the universe. But later, when the details from the CMBR came, the later data, it ruled out the cosmic string wakes to be the generator of the large-scale structure, but that does not necessarily mean that it did not contribute to the other parts of the evolution of the universe. Mostly, the density fluctuations would lead to large temperature fluctuations. And these temperature fluctuations would lead to disruption of subsequent phase transitions. One of the major phase transition is the quark-gluon plasma to hadron phase transition, where the neutrons and protons are produced, and small changes in temperature will change the neutron and proton ratio before nucleosynthesis. This will alter the relative abundance of the primordial elements during nucleosynthesis. As is well known, nucleosynthesis calculations are used as a benchmark for many theories. So the cosmic string wakes can also be used for trying to constrain due to the nucleosynthesis calculations. Now, all these signatures that I have been discussing till now, gravitational lensing, which is the primary signature, and the fact that cosmic strings also lead to B-mode polarization in the CMB sky. Recently also, there have been a systematic study of distinct patterns in the 21 centimeter redshift surveys. This is the study of neutral hydrogen. And if there is a three-dimensional wedge, as I mentioned, which has large overdensity of neutral hydrogen, then the absorption in that region would be much higher than the one in the rest of the background. This would leave very distinct patterns on the 21 centimeter maps. So all these that we are talking about involve density fluctuations of some kind of other. And these density fluctuations are also related to the temperature fluctuations. So there are line discontinuities in the cosmic microwave background, which can be due to temperature fluctuations. The thing is that all these things together seem to indicate there might be cosmic strings out there, but we do not have any definitive proof of whether these individual observations are indeed due to a cosmic string or due to some other object. So, though there are all these searches going on, it's also important to look for other distinctive features or other distinctive radiation, which will tell us whether it is coming from a cosmic string wake or not. So that is one of the motivations with which we will be looking at electromagnetic radiation in the region which is not in the optical range. This was previously only seen for superconducting cosmic strings. So as I mentioned before, there are many different kinds of cosmic strings, and one of them is the superconducting cosmic strings. These strings have an electric current flowing along the length of the string. So when this superconducting string moves through the plasma, they generate a magnetic field. When a magnetic field is generated in the plasma, it gives rise to a host of many observations such as synchrotron radiation, gamma ray bursts, fast radio bursts, and a lot of other things which have all been attributed to the superconducting strings. However, the superconducting strings can only be generated in some specific phase transitions. So therefore, these superconducting strings can be only associated with a particular phase transition. We would like to look at strings which are not superconducting, which do not have an electric current flowing through it. And we chose the abelian Higgs cosmic string, a stable cosmic string with a fixed radii, to study how particles move around in the cosmic string background. One of our first studies showed that if there are randomly scattered particles around an abelian Higgs cosmic string, the particles tend to get trapped in bound orbits. It has already been shown by previous authors that there are the orbits of particles around cosmic strings can be bound, unbound, and part of the reason why some are bound and some are unbound are due to the angular momentum and the energy of the particles. So we did a study where we put in certain angular momentum and energy of particles so that they get caught in the bound orbits, and found that around a cosmic string, it is possible to generate small fluctuations, density fluctuations, or density inhomogeneities. So the particles are clustering close to the cosmic string. This clustering of particles leads to currents around the cosmic string. Now, we also looked at electron and positron currents, but the electron and the positron currents will neutralize each other. However, the neutrino current is not neutralized. So we do get a neutrino current around abelian-Higgs cosmic strings, and we have calculated the current density as a function from the distance from the cosmic string. As we can see that closer to the cosmic string, there are more neutrinos, whereas as we move far away, the neutrino density goes down. So there is a gradient of neutrino density close to the cosmic string. The early universe plasma has basically leptons and quarks. This is before the hadronic phase transition. So we have only the leptons and the quarks. Among the leptons, the electron and the neutrinos are the major leptons which interact with each other. Now, the neutrino gradient, if it is generated, it would obviously exert a force on the electrons, and it will push away the electrons into other regions. So if there is a density gradient in the electrons, in the neutrinos, it will lead to a density gradient in the electrons. This causes an electron density inhomogeneity in the plasma. We have considered the plasma to be stable. We have not considered any instabilities. The instabilities may form behind shock waves, but for our work, we have not considered any instabilities. A stable plasma is taken, which has the neutrino and the electrons, writing down the continuity equations and the momentum equations for both of these electrons and the neutrino, as well as the field equations. We can find out a relation between the Nu, which is the number density of neutrinos, and the Ne, which is the number density of electrons. Omega p over here is the plasma frequency. So as you can see, if delta Nu is non-zero, it will automatically lead to a non-zero value of delta Ne, and an electromagnetic potential is generated. If an electromagnetic potential is generated in the shock wave behind a string, then it is possible to generate a magnetic field using the Biermann battery mechanism. The main equation for the Biermann battery mechanism is given over here. As you see, the evolution of the magnetic field is dependent on the magnetic field in the first three terms, while the fourth term does not have a magnetic field. It is only a density gradient of electrons and a density gradient of temperature. So if the magnetic field is completely zero, then a magnetic field can be generated from the fourth term of the Biermann equation, and this is what is known as the Biermann battery mechanism. The gradient of the temperature will always be present because it's a shock wave, and a shock wave has a temperature gradient across the shock. The electron gradient is generated due to the neutrinos, which we have discussed before. So the last term in this Biermann battery mechanism becomes non-zero. This is a sketch of what is happening in the cosmic string wave. The neutrino overdensities are denoted by the straight lines. Due to the presence of those overdensities, the electrons are being pushed into troughs, thus creating a density gradient, which is here as a simplification, it is shown to be perpendicular to the temperature gradient. It may not be exactly perpendicular, there might be an angle between them, but a magnetic field is generated. We also made a general estimate for the magnetic field, and we found it to be of the order of 10 to the power 13 Gauss at the electroweak scale. At the electroweak scale, the universe size is very small. So that is why apparently it looks quite high, but it's not very high because the universe will expand. And as the universe expands, the magnitude of the magnetic field will be going down. So 10 to the power 13 Gauss field will be negligibly small at the current scales. Therefore, it's a very low field that is being generated, but still it is a non-zero field that is being generated in the wake of the magnetic field. So right at the early stages of the universe, we see that a magnetic field is generated in the wake of a cosmic string. This seed can act as a primordial field, seed primordial field. It may get enhanced by turbulence as the cosmic string moves through the plasma. Since the electroweak scale is a very early scale, we would like to study what happens at later times. That is the times when we can make some observations about the going on in the universe. So we started looking at the cosmic string wakes in the presence of the magnetic field. As I've mentioned before, all the previous studies of wakes were usually for the hydrodynamical study, and nobody had, except for superconducting strings, for the other kinds of cosmic string, nobody had really looked at the magnetohydrodynamic part of the cosmic string wake. So we used available magnetohydrodynamic code, OpenMHD, to evolve these structures, these wakes. The code does not have any dynamo mechanism, so we do not get very significant magnification of the magnetic field. But even without the magnification of the magnetic field, we do get very interesting realignments due to the shocks in the wake structure. I will just mention very briefly the OpenMHD code, which we had been using, and how we have modified it for the cosmic string case. So the OpenMHD code solves the linearized MHD equations when there are small perturbations given to the fluid flowing through a given volume. The equations, some of the equations are V1, V1 and ρ1, all those are the perturbed quantities. Now, the way the code is written, we have modified the boundary conditions so that the perturbations are the perturbations that would happen in the cosmic string matrix. So we have a cosmic string and we have placed it at a position. While the particles are flowing beside the cosmic string, we give them a velocity perturbation. If you recall, in the initial slides, I had said that a cosmic string gives a velocity perturbation to particles going beside it. And this velocity perturbation is dependent on the deficit angle of the cosmic string. For visualization purposes, we have, of course, kept a larger deficit angle. However, we have checked that on scaling, the answers remain the same. For example, if we have an opening angle of 15 degrees and 5 degrees, the corresponding results would not be different. They will only be scaled by a scale factor. So that is why it does not matter if you have a slightly larger opening angle for the cosmic string. So basically, that is what we have done. We have put open boundary conditions, and we have given a small velocity perturbation after it enters when it comes close to the cosmic string. And as you can see from the streamline structure over here, over time, what happens is that the particles move around and form vortical structures. So this is where a pair of vortices have been formed because there is an angular momentum which is coming in due to the perturbation to the velocity. We also have given perturbations to the magnetic field, different perturbations, and we'll discuss them as we go along, and the results that come from these different perturbations. Before that, one of the interesting things that we had found out was that there were multiple shocks which we were able to identify in the numerical simulation. Now, as is well known in magnetohydrodynamic simulations, the shocks can be identified by a sharp change in the velocity, pressure, and density simultaneously. The analytical calculations come from the Rankine-Husson conditions, and we have identified multiple shocks as well as neutral points and magnetic reconnection loops. So I will go back to this slide. And if you see, there is a symmetry across the zero axis. And in the lower diagram, we see very clearly two magnetic loops being formed. Whereas in the first upper diagram, we had the magnetic field lines which were going as straight lines. So this is what is called the phenomenon of magnetic reconnection, which I will come back to in a few more slides. So the first thing that I would like to discuss is the amplification of the magnetic field due to shear perturbations. Now, in the code that we had, the OpenMHD code, as I mentioned, there is no turbulence, or there is no extra energy term which would give rise to amplification of the magnetic field. However, we know that shear perturbations do give rise to an increase in magnetic field, and when we put in two different kinds of shear perturbations, we do find that the peak magnetic field evolves to a larger and larger value. And these are the two perturbations which we have used. One is along the flow axis. Bx over here is the axis along which the fluid is flowing, the cosmic string is moving. By is the transverse axis. And we have taken two different kinds of perturbations. In the first perturbation, we have Bx is equal to B0 e to the power minus alpha y, whereas By is kept as it is. And in the second one, the By is perturbed and the Bx is just the flow. So we have taken transverse and longitudinal perturbations to the magnetic field. And what we find is in both the cases, for different values of alpha and beta, we get an amplification of the magnetic field. This is not too surprising because from Alfvén's theorem, we know that the magnetic field lines are usually frozen in the fluid. So they flow with the fluid. Frozen means the flow with the fluid. So when the area is constricted, the magnetic field expands. So over here, since we are generating an overdensity, we will get a higher field. So this is how the field is getting amplified without the presence of a dynamo mechanism. Usually we need a dynamo mechanism, but this code does not have a dynamo mechanism. So what is happening is that the plasma bends around the cosmic string and the field lines get distorted. We can define what is called a deformation tensor, where delta xi is the older field lines, whereas delta qj is the new field lines after deformation. And since volume is conserved, the deformation tensor itself is related to the volume. From Alfvén's theorem, as we know, the magnetic field into the area is a constant. So based on that, we can come to the final formula that the final field will depend upon the density of the final field by the density of the initial field. Here, of course, we are assuming that the L initial and the L final are more or less the same. As I have mentioned, the deformation is very, very low. So therefore, because of that, we can say that the final field will definitely depend upon the overdensity that is generated by the wake. So therefore, we can say that an overdensity has been generated by the wake. Now, while we found that there is an amplification of the field, we also found that for certain values of beta, there is no amplification. On the other hand, the magnetic field decays rapidly. Beta, if you remember, is the length scale of the perturbations in the transverse direction, so y direction. So we understand that whatever perturbations we give along the flow of the liquid or fluid, that perturbation will always enhance the field. But the perturbations we give perpendicular to the flow may or may not cause amplification of the field. And we also found out the values of beta for which this decay comes. And we find that it is approximately related to the gyro radius of the particle. This we already had read in the literature that Alfvén's theorem can break down even for ideal plasmas. Alfvén's theorem does break down for resistive plasmas, but even for ideal plasmas, Alfvén's theorem can break down at small length scales. Over here, it looks like that small length scale in our case is the gyro radius. And again, that can be explained through the notion of a guiding center, which is often used when we used Alfvén's theorem. So the notion of a guiding center says that the flow of electrons in the plasma can be understood in terms of a guiding center. That means the particle will move in a gyro motion around a guiding center, and the guiding center itself will move with another velocity. The two velocities are given over here, Vg and Vc. Vg is the gyro motion velocity, Vc is the velocity of the guiding center itself. However, all these things are valid only when the length scale of the system is much, much bigger than the gyro radius. So therefore, otherwise you see the definition of the gyro frequency or the gyro radius is only there for a constant magnetic field. So therefore, that thing will not hold, and this expression for Vg will not come out. So we must have the length scale of the system much, much greater than the gyro radius. But it seems that when we give the perturbation, if the perturbation comes to be of the scale of the gyro radius, then Alfvén's theorem is no longer holding, and it is breaking down, even though we have an ideal plasma. For resistive plasmas, Alfvén's theorem does break down, but this is also happening for an ideal plasma. That means there is the possibility of magnetic reconnection even for an ideal plasma. And that is where we'll come to. I'll very briefly say what is magnetic reconnection. It is a very well-known concept in magnetohydrodynamics, but I will still mention it once. So the process of magnetic reconnection happens in highly conducting plasmas. What happens is that if there are two oppositely directed magnetic fields and they come very close together, then it is possible for the magnetic lines of force to break free and reconnect again, thus changing the basic topology of the magnetic field. And this we have already seen in our simulations, where we started off with magnetic fields which were all parallel to the flow of the fluid, and we ended up with loops of magnetic reconnection. So therefore, the basic topology of the magnetic field had changed during the evolution of the cosmic string wake. We then studied it using analytical work. So we look at the field that is generated due to the Biermann mechanism in the shock of the cosmic string. That is how we started off. And we noticed that the temperature gradient are on the two sides, which makes the magnetic field pointing on two opposite sides. So you see the density gradient is along the x-axis. It is along the axis along which the string is moving. And the magnetic field, which is generated along the z-axis, will be pointing upwards in one case and downwards in another case. Of course, it is slightly away from each other because they are generated at the two shock fronts, and the two shock fronts are separated. But as we know, the shock fronts move towards each other, so the magnetic fields are squeezed together. And we know that the width of the cosmic string is rather narrow. So therefore, the two shock fronts will be pushed together and they will come together, and you will find that magnetic reconnection occurs. So the motion of the two shock fronts towards each other will generate a magnetic reconnection. So that is why that happens when we give a perturbation along the y direction, that is perpendicular to the motion of the cosmic string. That is what pushes the shock fronts to come together and to generate a magnetic reconnection. So we use the simplest model of magnetic reconnection. There are many models of magnetic reconnection which are used because there are still a lot of work going on in how to understand magnetic reconnection. It is a well-known subject in solar physics. So a lot of models are out there, but we chose the simplest model, the Sweet-Parker model of magnetic reconnection, to model the magnetic reconnection in the cosmic string wake. It's a quasi 3D model of magnetic reconnection. And we find the velocity with which the magnetic field lines move closer together. The velocity depends on the gradient of the magnetic field along the x-axis, del x, bx, del y. That is why, as you see, the shear perturbation is important. These lines meet and reconnect, resulting in the generation of a large amount of kinetic energy. The kinetic energy released depends on the magnetic field and the plasma density, as well as the length of the reconnection region. Interestingly, what we have found out that if the cosmic strings would survive to the later stages, for example, redshift of about 30, that is what can still be observed, then the energy flux, if we can calculate it, we find that it is of the order of 10 to the power 14 erg per centimeter square. This is a very, very large amount of energy, and it will accelerate the plasma particles. The interesting thing was that the energy gamma ray bursts, which have been observed with energies of 10 to the power minus 5 per centimeter square, and the time scales of these GRBs are of the order of 0.1 seconds to 30 seconds, which is of the same order as the shock velocities for the two shocks to come and collide in the magnetized wake of the cosmic string. So using the Sweet-Parker model, the simplest model of reconnection, we have been able to show just of the order of magnitude calculation that it is possible to have a gamma ray burst in the wake of a magnetized cosmic string. So the magnetic reconnection in cosmic string wakes can be a progenitor for a GRB. Currently, we are still working on this. We also look for other possible signatures of cosmic strings, which come due to the presence of the magnetic field in the wakes. As we have already seen, multiple shocks can occur in the wakes. These can lead to shock-shock collision. These shock-shock collisions can lead to gravitational waves. Other than this, the energy deposited in the wake region may also accelerate charged particles, both electrons and ions. As the charged particles are accelerated in the magnetic field, they will generate synchrotron radiation. The synchrotron radiation emitted by relativistic electrons from various places in the universe is observed and is well studied. We have also studied this synchrotron spectrum from the electrons which are there in the wake of a cosmic string. We have used the standard formulas, and the N over here is the total number of electrons in the cosmic string wake, which can be obtained from the volume of the wake and the number density of the electrons. We can find out the total energy of the electrons in the string wake. And since, as we can see, it depends on the redshift parameters, we have tried to find out numerically the spectrum for different redshift values. For this, we also, excuse me?
Sorry, we have 1 minute. You have 1 minute.
Okay. I'll just wrap up. So here this is the total energy from the synchrotron spectrum. I'll leave out the details and go directly to the spectrum itself. We can see that the spectrum for different values of Z are plotted over here, and they have a distinctly different pattern from those from blazars and GRBs. They are fitted by 3 different power laws. And interestingly, we also looked for several unknown sources in different standard online catalogs for values of Z equal to 1. And we found some points which are in the range that we have generated the graphs. So this is a very simplified models, and there are several things that still need to be done. Since I am running out of time, I will summarize the talk and then talk about the new possibilities. So I have just talked about topological defects, which will form at symmetry breaking phase transitions. As I hope I have been able to convey, the cosmic string defect has the highest probability of being detected. And though there are gravitational signatures which are being used to search for cosmic string defects, it would be really very interesting if we can have various different kinds of signatures, not only of the density inhomogeneity in the cosmic string wake, but of also the magnetic field and other features that this cosmic string can bring in. Since now we have shown that there is the possibility of having a magnetic field in a cosmic string wake, which does not have an electric current passing through it, which is not a superconducting string, this method that we have talked about will work not only for abelian Higgs strings, but any cosmic string which has a finite radius. So as long as we have a stable cosmic string, we can generate a magnetic field in its wake. And it looks like if we look for signatures from these different parts of the radiation spectrum also, then we might be able to narrow down the already proposed observations to a few of them, or we can definitely say which of them are giving rise to these observations. So the path forward, currently, as I've mentioned, the GRBs are the most interesting thing because we have seen that we are able to get the energy, the fluence. What we are currently trying to do is trying to match exact observational curves, the light curves of GRBs, to the magnetic reconnection in cosmic string wakes. Our current simulations, of course, can be improved upon a great deal. There are several approximations which we are using. For example, we are looking at synchrotron radiation from one single wake only in a certain region, which may not be the proper way to look for it. And maybe it would be better if you have a network of strings. So all those can be incorporated. Another important aspect that we have not even discussed in this talk is the turbulence and the dynamo mechanism, which can again happen in the wakes of cosmic strings. We plan to look at these magnetic reconnection in the presence of turbulence and the dynamo mechanism, which will give us a better picture of what to expect in the gamma ray bursts. And it looks like if we involve all the range of electromagnetic radiation from the full length of the radiation, not only the optical range, but also the other ranges, the gamma range and other ranges, we may be able to obtain a more definitive signal for cosmic string wakes. And at the end, it is with great joy I would like to acknowledge DST SERB, Government of India, who have supported this work through the Power Grant SPG 2021. My research scholars, Shobhan, Abhishek, both of whom have graduated now, and my current research scholar, Shoman and Dilip. Nearly all the work have been done by these 4 people. Thank you all.
Okay, thank you, Professor, for the nice talk. So, if the audience has any question, please unmute yourself and ask. Okay, if the audience has no question, I have a question. So, during your this shear pressure, shear thing, you took exponential alpha minus alpha x or minus alpha y.
Yes.
If I would took if minus alpha x square or minus beta y square, something like that, what would happen?
So basically, we haven't tried alpha x square, but we have tried some other harmonic perturbations also. We find similar results as long as they are harmonic. We haven't tried any anharmonic perturbations as yet. So therefore, I'm not sure what will happen. I believe it will lead to more interesting results. But till now, we have only tried harmonic perturbations. But any harmonic perturbation you can take, and it really leads to more or less the same results.
Harmonic means alpha is imaginary, right? Alpha or beta,
it's
whatever.
oscillating, hyperbolic or something like that. So it can be alpha x or I alpha x, or it can be written down as sine and cosine functions, or sine hyperbolic or cosine hyperbolic functions. That's what I mean by harmonic. Yes.
Okay. Okay. Thank you. So, if there is any other question from the audience? Okay. If there is no other questions, let us thank the speaker.